Dark matter is one of the most elusive and perplexing concepts in contemporary astrophysics, a form of matter that neither emits nor absorbs light, rendering it effectively invisible to conventional observational methods. Yet, despite its mysterious and intangible nature, dark matter constitutes a staggering 85% of all matter in the universe, profoundly shaping the cosmic structures we observe. The first hints of dark matter emerged in the 1930s when astronomer Fritz Zwicky studied galaxy clusters. He noticed a strange discrepancy. The galaxies within these clusters were moving at velocities much higher than those predicted by the visible matter alone. If only luminous mass were present, gravity would not be strong enough to prevent these clusters from dispersing. Zwicky concluded that some unseen dunkle materie, or dark matter, was holding these massive structures together. Decades later, astronomer Vera Rubin reinforced this theory with her observations of galaxy rotation curves. Rubin and her colleagues found that stars in spiral galaxies moved at nearly constant speeds, regardless of their distance from the galactic center. This contradicted predictions based solely on visible matter, where stars farther from the center should orbit more slowly. The only explanation was the presence of a massive, invisible halo of dark matter enveloping galaxies, providing the gravitational glue necessary to maintain their structural integrity. But what exactly constitutes dark matter remains an open and tantalizing question. Physicists propose several candidate particles to explain this invisible substance. Among the most prominent theories are weakly interacting massive particles, WIMPs, hypothetical particles that interact with ordinary matter only via gravity and the weak nuclear force, making their detection exceedingly challenging. Another intriguing candidate is axions, extremely light and weakly interacting particles theorized to resolve problems in quantum chromodynamics. Alternatively, massive astrophysical compact halo objects, MACHOs, dense objects such as black holes, neutron stars, or faint white dwarfs, were once considered as dark matter candidates, though extensive searches have largely ruled them out as the primary constituents. Observational techniques have significantly advanced, yet direct detection of dark matter remains elusive. Current experiments involve detectors placed deep underground, shielded from cosmic rays, searching for rare interactions between dark matter particles and ordinary atomic nuclei. Observatories in space also investigate indirect signs, looking for excess gamma rays, neutrinos, or cosmic rays that might result from dark matter particle annihilations. Yet, despite rigorous experimental efforts, dark matter has so far evaded direct confirmation, leaving astrophysicists and cosmologists navigating in the realm of theoretical inference and indirect observation. Dark matter's influence is not limited to galaxies and clusters alone. On cosmic scales, it shapes the large-scale structure of the universe itself. In the early universe, slight density fluctuations in dark matter served as gravitational wells, attracting ordinary matter and eventually leading to the formation of galaxies, stars, and planetary systems. Without dark matter, simulations indicate that the universe would lack the complex filamentary structures observed today, galaxies would never coalesce, stars would fail to form, and life itself might never arise. Moreover, gravitational lensing, the bending of light by massive objects, provides another crucial observational signature. Observations of distorted and magnified images of distant galaxies and quasars have consistently demonstrated more mass in galaxy clusters than visible matter alone can account for. This excess gravitational effect provides compelling indirect evidence for dark matter's pervasive presence. Cosmological observations, Notably, measurements of the cosmic microwave background radiation by satellites such as Planck and WMAP independently confirm dark matter's essential role. These precise observations indicate that ordinary matter comprises only about 5% of the total energy content of the universe, with dark matter making up around 27%, and the mysterious dark energy accounting for the remaining 68%. This consistent agreement across independent observational methods strengthens the argument for dark matter's reality and necessity. In sum, dark matter is indispensable, holding cosmic structures together, shaping the formation of galaxies, and influencing the very evolution of the universe. Its nature remains one of modern science's greatest mysteries, fueling extensive research across multiple scientific disciplines. The existence of dark matter highlights a profound truth: the visible universe we observe and understand is but a small fraction of the cosmic tapestry. A vast portion remains invisible, detectable only through its gravitational influence on the matter we see. The scientific quest to identify and understand this enigmatic component continues to push the boundaries of physics, cosmology, and our understanding of the universe. In recent years, astrophysical simulations have become increasingly sophisticated, attempting to replicate the universe's evolution by incorporating different scenarios and properties of dark matter. Such simulations have consistently demonstrated that dark matter is critical not only in holding galaxies together but also in facilitating their very formation. Without its gravitational scaffolding, normal matter would remain too diffuse to collapse into the dense regions necessary for stars to ignite and galaxies to assemble. This indispensable role underscores dark matter's foundational status in the cosmic framework. An intriguing new area of research explores how variations in dark matter properties could alter galaxy formation and evolution. For instance, self-interacting dark matter, SIDM, a variant hypothesis suggesting dark matter particles occasionally collide with one another, offers solutions to specific problems arising in galaxy formation models. Such interactions might explain observed discrepancies in the density profiles of dwarf galaxies, which appear less dense at their centers than simulations based purely on non-interacting dark matter predict. Researchers continue to refine these models, using observational data to constrain the possible interactions and properties of dark matter particles. Another important observational approach involves examining dwarf galaxies orbiting larger galaxies, such as the Milky Way. These satellite galaxies, often rich in dark matter relative to their luminous matter, serve as natural laboratories for studying dark matter properties. Their dynamics, influenced heavily by unseen mass, offer clues about dark matter's distribution and behavior on smaller cosmological scales. The detailed mapping of satellite galaxies provided by missions like Gaia has already yielded invaluable insights, challenging existing models and stimulating new theories of dark matter's nature and interactions. Additionally, cosmologists and physicists consider the role of dark matter in the context of broader theories of particle physics and fundamental forces. For example, extensions to the standard model of particle physics, such as supersymmetry, predict new particles that naturally fulfill the criteria for dark matter candidates. While particle accelerators like the Large Hadron Collider, LHC, have yet to uncover direct evidence of such particles, ongoing experiments remain vital in narrowing down theoretical possibilities, continually testing and reshaping our understanding of fundamental physics and cosmology. Gravitational wave astronomy, an emerging field opened by LIGO's groundbreaking detections, also offers novel opportunities to probe the nature of dark matter. Mergers of compact objects, such as black holes or neutron stars, provide indirect constraints on the presence of dark matter through careful analyses of gravitational wave signals. The environments surrounding these cataclysmic events could potentially contain significant amounts of dark matter, influencing merger rates, wave signatures, and the precise nature of the observed signals. Thus, gravitational waves serve as a new observational window, complementing traditional electromagnetic and particle detection methods. Furthermore, future missions, such as the Euclid Space Telescope and the Vera C. Rubin Observatory, formerly LSST, promise groundbreaking observational data with unprecedented precision and depth. These observatories aim to map billions of galaxies, measure cosmic expansion, and precisely trace the distribution of dark matter throughout the universe. Such large-scale surveys will profoundly enhance our understanding, enabling scientists to rigorously test dark matter theories, constrain particle physics models, and potentially revolutionize our knowledge about this mysterious cosmic ingredient. At its core, the study of dark matter reveals a deeper philosophical insight into the scientific pursuit itself, humanity's ongoing quest to comprehend phenomena beyond immediate sensory experience. The existence of an invisible, pervasive substance that dominates cosmic structure reminds us that much of reality transcends visible boundaries, lying in realms accessible only through rigorous scientific inference, advanced technology, and creative theoretical modeling. Thus, dark matter epitomizes the inherent beauty and complexity of the universe, reflecting a fundamental truth: our observable reality, rich and detailed as it appears, is only a fragment of a much larger, more enigmatic cosmos awaiting discovery and understanding. The quest for dark matter not only reshapes our understanding of the universe but also poses fundamental questions about the limits of scientific knowledge itself. As scientists strive to unravel its nature, they confront both technological limitations and conceptual challenges, continually pushing forward the boundaries of observational astrophysics, particle physics, and theoretical cosmology. One particularly compelling avenue of contemporary research is the investigation of primordial black holes, hypothetical objects formed immediately after the Big Bang, as potential dark matter candidates. Unlike conventional stellar black holes, primordial black holes could exist across a vast range of masses and remain virtually undetectable except through their gravitational interactions. Recent gravitational lensing studies and gravitational wave detections have sparked renewed interest in this scenario, raising the intriguing possibility that dark matter might not be an exotic particle, but rather remnants from the universe's earliest moments, silently shaping cosmic evolution from the shadows. Parallel to these theoretical developments, laboratory-based experiments continue to innovate with cutting-edge detection techniques. Facilities such as Xenon, LUX Zeppelin, and the Future Darwin experiment utilize massive vats of ultrapure liquid xenon deep beneath Earth's surface, shielded from cosmic rays and background radiation, to capture elusive interactions between dark matter particles and atomic nuclei. These experiments operate on the premise that, despite dark matter's rarity of interaction, occasional collisions with ordinary matter must inevitably occur, detectable through minute energy transfers. Each year, these detectors grow in scale and sensitivity, incrementally increasing the likelihood of identifying a direct dark matter signature, an event that would revolutionize astrophysics and particle physics alike. Space-based observatories, including missions like the Fermi Gamma Ray Space Telescope and future initiatives such as the proposed eAstrogam and AMS-02 aboard the International Space Station, contribute significantly to indirect dark matter searches. By scrutinizing the gamma ray emissions from the centers of galaxies, dense dark matter halos, and galaxy clusters, astrophysicists hope to detect anomalies indicative of dark matter particle annihilation or decay. Although controversial claims and potential signals, such as the gamma-ray excess from the Milky Way's galactic center, have emerged, conclusive evidence remains elusive, highlighting the ongoing complexity and subtlety of dark matter interactions. Additionally, astronomical observatories employing next-generation radio telescopes, like the Square Kilometre Array, SKA, promise unparalleled sensitivity in mapping hydrogen gas distributions throughout the cosmos. By tracing hydrogen movements influenced by dark matter halos in unprecedented detail, astronomers aim to reconstruct dark matter structures in the universe's early stages, illuminating how this unseen component guided the initial formation and evolution of galaxies and large-scale structures. Furthermore, interdisciplinary collaboration has become crucial, blending astrophysics, particle physics, cosmology, and computational sciences. International teams working across continents unite expertise to run sophisticated simulations, conduct exhaustive observational campaigns, and interpret complex data sets. This collaborative model enhances scientific rigor and accelerates progress, emphasizing the global importance and profound implications of solving the dark matter puzzle. Ultimately, the search for dark matter resonates far beyond academic curiosity. Understanding dark matter's nature could provide key insights into the underlying fabric of reality itself, potentially reshaping our comprehension of fundamental physics, gravity, and cosmological evolution. It also embodies a broader narrative of human exploration and discovery, our ceaseless drive to understand the unseen, probe the unknown, and continually redefine our place within the cosmos. Dark matter, a phenomenon that we cannot directly see yet unmistakably detect through its gravitational footprints, symbolizes our collective aspiration to uncover deeper universal truths hidden beneath the visible veneer of the universe. As the investigation deepens, alternative and even radical hypotheses continue to emerge. Some researchers propose that dark matter may not be a particle at all, but rather a signal that our current understanding of gravity is incomplete. Modified Newtonian dynamics, MOND, and its relativistic extensions, like TeVis, suggest that gravity behaves differently on large scales than predicted by Einstein's general relativity. These theories attempt to explain galactic rotation curves and cosmic structure formation without invoking dark matter, instead modifying the laws of motion or gravity. While these models can replicate certain observations, they often struggle to explain the full range of cosmological data as effectively and consistently as the dark matter framework. Nonetheless, the persistence of such alternatives keeps the scientific debate alive and stimulates critical re-examinations of foundational principles. Even within the standard lambda-CDM, lambda-cold dark matter, cosmological model, refinements continue to be made. The model posits a universe composed primarily of cold, i.e., slow-moving, dark matter and dark energy, represented by the cosmological constant lambda, which drives the accelerating expansion of the universe. This model has proven remarkably successful in explaining the large-scale structure of the cosmos, the anisotropies in the cosmic microwave background, and the distribution of galaxies. However, discrepancies at smaller scales, such as the core-cusp problem and the missing satellites problem, challenge the model's completeness and motivate the exploration of alternative forms of dark matter, including warm dark matter and fuzzy dark matter, hypothetical particles with quantum properties that could smooth out small-scale structure. Beyond theoretical and observational science, dark matter inspires a profound sense of wonder in both the scientific and philosophical communities. It forces us to grapple with the idea that the overwhelming majority of matter in the universe is invisible, untouchable, and perhaps fundamentally unknowable with current tools. This has philosophical implications for how we define reality, how we interpret observation, and what it means to know something in science. It challenges the assumption that what we see is all there is, reminding us that the cosmos is deeper, darker, and more complex than human intuition often allows. Dark matter also feeds the human imagination, appearing in science fiction, art, and metaphor. In literature and film, it is often portrayed as a source of hidden power, a key to unlocking alternate realities, or a veil concealing ancient secrets. While these creative interpretations diverge from the rigor of science, they reflect a cultural resonance with the mystery and allure of the unknown. This public fascination drives curiosity, education, and support for scientific research, linking the pursuit of dark matter to broader human narratives of exploration and discovery. In educational contexts, dark matter serves as a gateway for engaging students and the public with astrophysics and cosmology. Its very invisibility makes it an ideal starting point for teaching the importance of inference, evidence, and critical thinking. Through simple analogies, such as seeing a ship's wake without seeing the ship, educators help illustrate how unseen forces can be studied through their effects. In doing so, dark matter becomes not just a research topic but a powerful teaching tool, bridging abstract concepts with tangible reasoning. As humanity's tools grow more precise and our theories more refined, the veil may one day lift, revealing dark matter in its true form. Whether it turns out to be a new type of particle, a primordial remnant, or a paradigm-shifting force beyond known physics, the discovery will mark a pivotal moment in the story of science, a moment comparable to the understanding of atoms, the discovery of galaxies, or the unveiling of the cosmic microwave background. And yet, even if dark matter remains hidden for decades to come, its gravitational influence continues to sculpt the universe around us. Every galaxy, every cluster, every filament stretching across the cosmic web is a silent testament to its presence. It surrounds us, permeates space, and binds the cosmos together, not as a shadow, but as a silent architect of cosmic destiny. This silent architect, though invisible to our eyes, has become one of the most profound revelations of modern science, a reminder that much of existence lies beyond the reach of light. The universe, once thought to be a luminous expanse of stars, galaxies, and nebulae, is now understood to be largely defined by what cannot be seen. The stars are mere tracers, drifting through the deeper gravitational seas sculpted by dark matter. In this unseen realm, galaxies take shape, dance, collide, and evolve over billions of years, following paths charted by this hidden mass. On the largest scales, dark matter is the skeleton of the cosmos. It outlines the vast cosmic web, a structure that connects galaxy clusters across unimaginable distances through filaments of dark matter and gas. Observations from weak gravitational lensing and large-scale surveys reveal the intricate geometry of this web, hinting at a deep underlying order. These colossal structures formed not from light, but from the primordial density fluctuations in the early universe, fluctuations amplified by the pull of dark matter long before stars ever ignited. Even the fate of the universe may be intertwined with the properties of dark matter. Its interplay with dark energy influences cosmic expansion, structure formation, and thermal evolution. If dark matter decays over time, or if it interacts in subtle, yet undiscovered ways, it could affect the longevity and ultimate shape of the cosmos. The balance between dark matter and dark energy may determine whether the universe continues expanding forever, slows into a gentle freeze, or tears itself apart in a dramatic finale. Meanwhile, at the scale of galaxies, dark matter protects and preserves. It forms halos that cradle spiral galaxies like the Milky Way, stabilizing their rotation and preventing their dissolution. These halos extend far beyond the visible edge of any galactic disk, invisible yet dominant. Their mass dwarfs that of the stars and gas, their gravitational field reaching out into the intergalactic void, influencing the motion of satellite galaxies, stellar streams, and even intergalactic gas clouds. The patterns observed in these motions are among the most compelling proofs of dark matter's reality. At the smallest scale, dark matter raises the possibility of entire substructures that remain hidden, dark galaxies, devoid of stars, floating in the blackness between visible galaxies. These would be made entirely of dark matter, interacting gravitationally but never shining. Simulations predict their existence, and observational efforts are ongoing to detect their gravitational influence. If confirmed, such objects would redefine the taxonomy of galactic systems and hint at a vast population of unseen companions orbiting the luminous cosmos like silent sentinels. Perhaps the most humbling realization is this: we are not made of the dominant form of matter in the universe. Everything we see, our bodies, our planet, our sun, every star and nebula, constitutes a cosmic minority. Baryonic matter, from which all known life and chemistry emerge, is a mere sliver of the total mass energy budget. The vast majority is hidden, dark matter and dark energy forming the true foundation of the universe's architecture. We are built of stardust, yes, but we drift through a universe of shadows. And yet, within those shadows, we find the deepest light, not in the form of photons, but in the form of understanding. The search for dark matter is a journey not just through space, but through the limits of knowledge, the nature of reality, and the depths of human curiosity. It is a journey that unites experiment with theory, mathematics with mystery, and observation with imagination. A journey still unfinished. The journey into the heart of dark matter is not just an exploration of the cosmos, it is an unfolding dialogue between humanity and the unknown. With each new observation, we peel back a layer of the universe's hidden structure, only to find that beneath it lies an even deeper enigma. In many ways, dark matter is both a scientific puzzle and a philosophical mirror. It reflects our limitations, our questions, and our boundless desire to understand a cosmos that consistently escapes full comprehension. In the early universe, just moments after the Big Bang, dark matter was already playing a vital role. While photons and baryons interacted through radiation pressure, creating oscillations we now observe as temperature fluctuations in the cosmic microwave background, dark matter remained unaffected, silent and inert. It began collapsing into clumps, unaffected by radiation, forming the seeds of structure before light itself could freely move. These clumps served as the gravitational anchors around which ordinary matter would eventually gather. Without this early scaffolding provided by dark matter, the universe would have remained smooth and featureless, a vast expanse of drifting particles, too uniform for complexity to emerge. In this sense, dark matter is not merely a background component. It is the hidden hand that shaped everything we now observe. The galaxies we see today are the luminous peaks of vast, invisible mountains of mass. Their formation was choreographed by the gravitational wells carved out by dark matter long before the first atoms formed. Each star that ignites, each planet that forms, and every structure that emerges owes its existence to the guiding pull of this unseen presence. It is not a peripheral mystery, it is the foundation upon which the visible universe is built. And yet, for all its cosmic power, dark matter remains eerily silent. It does not radiate. It does not absorb. It passes through us, through stars, through entire planets without a trace. This ghostly behavior makes it profoundly difficult to study. But it also sets dark matter apart as a truly unique substance, unlike anything we know, and perhaps unlike anything we can imagine. Its resistance to detection has forced scientists to develop the most sensitive instruments ever constructed, capable of sensing even the faintest whisper of an interaction. But what if dark matter is more than just a particle? Some theorists have proposed that it could be part of a hidden sector, a parallel form of matter with its own forces, its own physics, perhaps even its own version of chemistry and structure. In such models, dark matter might interact with itself more strongly than it does with our ordinary world, forming dark atoms, dark stars, even entire dark galaxies that mirror our own in eerie, invisible silence. These shadow realms would be forever separated from us except through gravity, inhabiting the same space, but never touching, never glowing. The implications of this idea are staggering. It suggests that the universe could be far richer and stranger than we ever dared believe. That the visible cosmos we study with our telescopes is just one layer of a much deeper reality, a thin film of light drifting atop a vast, unseen ocean. In this context, dark matter is not just a component of the universe, it is a second cosmos hidden beneath our feet, all around us, and yet unreachable by light. If we ever manage to detect a dark matter particle directly, it would be a moment of monumental significance, on par with the discovery of the Higgs boson or even the Copernican revolution. It would confirm the existence of a new sector of nature, opening the door to a deeper understanding of the forces and symmetries that govern all matter. It could also lead to practical breakthroughs, new physics, new energy sources, new technologies born from an understanding of matter that was once hidden from view. But even if the nature of dark matter remains elusive, its effects are undeniable. It continues to guide galaxies, shape the cosmic web, bend light across billions of light-years, and whisper through the fabric of space and time. Its gravity is the artist behind the universe's great masterpieces, the spirals of galaxies, the lattice of filaments, the dance of clusters. To study dark matter is to embrace mystery, to walk a path lit not by answers but by questions. It is to accept that we do not yet see the full picture, and yet press forward with faith in the power of observation, mathematics, and imagination. In this pursuit, science becomes not just a method, but a kind of poetry, an attempt to hear the music of a universe that sings in frequencies beyond human ears. So we listen. We search. We build detectors in the silence of deep mountains. We launch satellites into the cold void. We run simulations across supercomputers that mimic the birth of galaxies. And with every step, we draw a little closer to the truth hidden in the dark. And still, we are only beginning to comprehend the depth of the unknown. For all the progress made, the true essence of dark matter remains just out of reach, a cosmic whisper we can follow but not yet grasp. Its presence is undeniable, its influence immense, yet its identity is veiled, like a word spoken behind glass. As we advance into the next decades, a new generation of instruments and missions will push the frontier even further. The Vera C. Rubin Observatory will scan the entire visible southern sky every few nights, creating a dynamic map of the universe and tracking how structures evolve over time, structures shaped by the invisible hand of dark matter. The Euclid mission, launched by ESA, will measure the geometry of the dark universe with exquisite precision, tracing the growth of cosmic structures across space and time. NASA's Nancy Grace Roman Space Telescope will observe gravitational lensing with unparalleled resolution, revealing the dark scaffolding that holds galaxies together. Each of these missions adds another brushstroke to the portrait of the unseen, layering data, refining models, and sharpening the contours of a shadow that stretches across the cosmos. And as our measurements improve, so too do our theories. Physicists refine models of dark matter self-interaction, test new symmetries, imagine connections with the early universe, and explore the possibility that dark matter may carry the echoes of cosmic inflation or phase transitions from the earliest fractions of a second after the Big Bang. Quantum theories of gravity, string theory, and extra dimensions also enter the stage, offering speculative but mathematically rich possibilities. Could dark matter be a portal to a higher dimensional structure? Could it be a manifestation of hidden symmetries, or a residue of multiversal interactions? While these ideas may seem fantastical, they are grounded in rigorous mathematics, guided by observational constraints, and serve as blueprints for what might lie beyond the current horizon of understanding. In parallel, the human story unfolds. The study of dark matter is not the work of isolated geniuses in ivory towers, but of global collaborations, physicists, engineers, computer scientists, and students working together across cultures and continents. Data flows across oceans. Discoveries are shared in real time. Young minds are inspired by the mystery of the invisible. In classrooms and lecture halls, the question, "What is dark matter?" ignites curiosity that echoes across generations. And still, behind this collective effort lies something deeply personal. The search for dark matter is, at its core, a reflection of our nature as seekers. We are drawn to the stars not only to map their light, but to understand what binds them together. We are not content with what is visible. We long to know what lies beyond. Dark matter, in all its silence, speaks directly to that longing. It reminds us that the universe is larger, stranger, and more beautiful than we imagined, that truth is not limited to what we can see, but includes what we can infer, what we can imagine, and what we can one day discover. The cosmos is not complete without its shadows. And perhaps we are not complete without the pursuit of them. For in chasing the darkness, we illuminate what it means to be human, to wonder, to question, to reach. As we peer farther into space, we also peer further back in time. Light from distant galaxies takes billions of years to reach us, and in that light we see echoes of the young universe, its turbulence, its birth cries, its first great structures arising. What we find again and again is that dark matter was already there. Long before stars were born, before the first galaxies took shape, dark matter had already begun weaving the invisible framework of reality. The James Webb Space Telescope, with its unparalleled ability to observe the earliest epochs of galaxy formation, is beginning to reveal galaxies from a time when the universe was only a few 100 million years old. Yet even these ancient structures appear too massive, too evolved, to have formed from ordinary matter alone. Their presence confirms what cosmologists have long suspected: dark matter accelerated the assembly of structure, allowing galaxies to emerge earlier and grow faster than visible matter would allow on its own. In this way, dark matter acts like a silent catalyst, enabling complexity, forging order from chaos, guiding the transformation of a smooth early universe into a vast, dynamic cosmos. And yet, it does so without light. That is perhaps its most haunting quality: it does not glow, and it does not shine. It is not radiant like the stars. It is not explosive like supernovae. It makes no sound and leaves no trail of color. But in its silence, it sculpts. In its stillness, it governs the motions of galaxies, dictates the shape of the web that binds them, and underwrites the expansion and evolution of the entire cosmos. Some have begun to wonder, could dark matter even influence life? If galaxies could not have formed without dark matter, then neither could stars, planets, or the environments in which life arises. In this indirect but profound way, dark matter may be a prerequisite for existence itself. Life, consciousness, even the act of observing the universe, all of it may be possible only because an invisible substance we cannot touch or see laid the foundation for cosmic architecture billions of years before we were born. This possibility elevates dark matter from a scientific curiosity to something more profound, a cosmic condition of our very being. The atoms that compose our bodies follow the gravitational paths determined by dark matter. Our Sun orbits the center of the Milky Way not in empty space, but within a dark halo of unseen mass. Every motion we make, every step, every breath, is part of a chain of consequences made possible by this mysterious matter. We are creatures of light, but we are held together by the dark. And still, we are just beginning to ask the right questions. What if dark matter interacts with dark energy in ways we haven't imagined? What if it has a complex internal structure, its own physics, its own laws, perhaps even its own forms of organization beyond anything we know? Some theories suggest it might clump, oscillate, form vortices, or exhibit quantum behaviors on galactic scales. Others explore whether the boundary between dark matter and ordinary matter is as clear as we think, or whether some forms of matter may exist in a liminal state, sharing properties of both. In the shadows, there may be layers of structure we cannot yet detect, echoes of higher dimensional geometries or hidden symmetries that tie together matter, energy, and spacetime in ways our current theories can only glimpse. These ideas stretch the imagination and the edges of our mathematics, but they reflect a larger truth: the universe is not finished revealing itself. And neither are we finished seeking. With every new telescope, every deep space probe, every underground detector, and every equation on a physicist's blackboard, we inch closer to the heart of the unknown. Perhaps we will one day isolate a dark matter particle in a laboratory, hold its signature in our instruments, and finally speak its name. Or perhaps it will forever remain beyond our grasp, a permanent veil that reminds us of the cosmos's infinite depth. As our knowledge expands, so too does our humility. For all our technology, for all our theories, there remains something almost sacred in the way dark matter refuses to reveal itself directly. It is as if the universe has written its story in layers, some bright and loud, others whispered in forces and distortions, felt but never seen. And dark matter is that whisper, echoing through every corner of the cosmos, a quiet rhythm beneath the brilliance of stars. When we look at the motions of galaxies, we are not just charting their paths, we are tracing the fingerprint of the unseen. When we observe clusters bending the light of galaxies behind them, we are witnessing space itself curve under the weight of something that does not shine. It is through these distortions and deviations that we come to know what we cannot see. In this sense, dark matter becomes a kind of cosmic poetry, written not in words, but in gravitational pull, in structure, in form. And yet, for all its power, dark matter is astonishingly indifferent. It does not burn, it does not bind into atoms, it does not form molecules. It flows through walls, through stars, through you and me, leaving no trace, save for its pull. It is a force without touch, a presence without light, and in that, it may be the purest form of being. Not as something that is, but as something that acts, a principle of motion, a sculptor of form, a silent hand behind the cosmic loom. This brings us to the deep philosophical questions dark matter awakens. What does it mean to be real? Is existence defined by what we can see, or by what we can measure, predict, and feel through its influence? Dark matter forces us to confront the limitations of perception, to accept that reality does not conform to human senses. It reminds us that we are creatures living in the light, but that most of reality exists in shadow, not in darkness as absence, but in darkness as mystery. In a strange way, the invisible world of dark matter reflects something within us as well. We too are shaped by unseen forces, memory, thought, gravity, time. We build cities, empires, civilizations, yet behind every act of creation there are deeper patterns, the mind's gravity, the soul's orbit, the unspoken structures of emotion and intuition. Dark matter in the universe, like the hidden frameworks within us, gives rise to all that is visible, meaningful, and alive. Perhaps this is why we are so drawn to it. Not just as scientists, but as humans. We look into the night sky and know instinctively that what we see is not all there is. That behind the starlight, behind the constellations and nebulae, lies something more, something deeper, older, essential. The dark is not to be feared. It is to be explored. It is the canvas upon which the stars are painted, the silence upon which the music of the galaxies plays. And still, the search continues. Beneath mountains, in the heart of detectors chilled to near absolute zero, deep in the dark of Earth and far in the black of space, we listen. We wait. We refine. Each failed detection is not defeat, it is progress, narrowing the possible, focusing the question. And each new signal, each anomaly, each unexpected twist in data, is a doorway. A whisper. An invitation. Dark matter may yet hold the key to unifying gravity with quantum mechanics, to explaining the fate of the universe, or even to discovering realms of physics we have not imagined. But beyond that, it holds a mirror to our essence, that we are beings who search, who question, who walk into the unknown not for answers alone, but because the act of seeking itself defines us. Each step into the unknown deepens our sense of awe. As we uncover more about the structure of the universe, we realize that dark matter is not an exception, it is the rule. The light of stars is the embroidery. The shadow, the weave. It holds the framework together. It is the gravitational skeleton upon which galaxies hang like lanterns. Without it, the universe would collapse into disorder, or never form at all. In a way, dark matter is the cosmos' most faithful guardian. Unchanging, silent, and constant, it shepherds stars along their orbits, it binds clusters into families, it supports the filamentous structure of the cosmic web. It asks for nothing. It simply is. Not as something to be seen, but as something to be trusted. For every time we measure the motions of a galaxy, every time we detect the bending of light, we reaffirm its presence. It has never failed us. It simply defies our reach. And perhaps it is not meant to be found easily. Perhaps dark matter teaches us the value of patience, of science not as instant revelation but as slow, persistent listening. The universe does not shout its secrets. It murmurs them across billions of years, in gravity, in structure, in silence. And we, small beings on a pale blue dot, have learned to hear that silence. In this silence there is beauty. Not the radiant beauty of a nebula or the explosive drama of a supernova, but the quiet, enduring beauty of presence without recognition. Dark matter, like deep time, like the void between galaxies, asks us to reconsider what matters. It invites us to wonder not only what the universe is made of, but why it is shaped this way at all. Are we here because of the conditions dark matter made possible? Was it the hidden hand that tilted the odds in favor of complexity, of chemistry, of life? Without its gravity, would the stars have gathered? Would planets have formed? Would biology have had a canvas on which to draw its blueprints? These are not just physical questions, they are existential ones. To understand dark matter is to ask how the visible and the invisible collaborate to produce a universe not only capable of stars, but of meaning. In the end, dark matter reminds us that there is more to existence than brightness and brilliance. That the most essential truths may lie in what cannot be seen, only inferred. That the invisible can be real, and the unknowable can be felt. And that perhaps, at the heart of the cosmos, there is not just energy or matter, but mystery itself. And so we search. We build instruments that listen for whispers in the night. We design algorithms that trace patterns in the chaos. We send questions into the dark, and we wait for the universe to answer in the language it speaks best: motion, gravity, structure, silence. For now, dark matter remains nameless. But it is not absent. It is the breath between the stars. The pause between each heartbeat of the cosmos. And it is calling, not to be solved, but to be pursued. Dark matter is more than a scientific mystery. It is a threshold. A liminal space between what we know and what we sense, between the illuminated world and the deeper forces that hold it in place. It does not reveal itself easily, yet it governs the grandest structures in existence. It does not shine, yet without it, there would be no stars to shine at all. It is the unseen weight of the cosmos, the silent architecture behind every galaxy, every cluster, every gravitational echo we can trace across time and space. Its influence is written into the rotation of spiral arms, the warping of spacetime, the dance of satellite galaxies, the very scaffolding of the observable universe. It holds everything, and yet, it withholds itself. In its elusive nature, dark matter teaches us something profoundly human, that truth is not always visible, and meaning is not always found in what is bright. That there is value in searching, even when the object of our search evades us. That some of the most powerful forces in existence are silent, invisible, and endlessly patient. And so, our journey continues. Each generation of scientists adds a new lens, a new theory, a new question to the long unfolding story. Each failure to detect becomes a refinement. Each anomaly becomes a clue. In caverns beneath the earth, in satellites above the atmosphere, in supercomputers that simulate the universe from its first moment to its distant future, the search persists. Not because we are lost, but because we are drawn forward by the very gravity of not knowing. For what is dark matter if not a symbol of the vastness that remains? A reminder that we are still discovering what the universe is made of, and perhaps, what we are made for. We are being shaped by curiosity, pulled by mystery, made restless by the horizon. And so we reach, always further, always deeper, into the space between light and shadow. Maybe one day we will name it. Maybe we will hold a particle in our hands, or map its structure with perfect precision. But even if we never do, dark matter will remain, the invisible foundation, the quiet force, the hidden story behind all that is. A story not of darkness, but of depth, of structure, of wonder, and of the beautiful, endless act of reaching into the unknown.